Hey guys, welcome back. We're moving right along. Up next, we're going to have Jordi Baylina talking about a zkVM foundation for next generation apps.
Hello, everybody. I'm Jordi Baylina from ZisK. Very quick. I mean, ZisK is, as you know, is 64 bits zkVM. It's a RISC-V based, and the main properties as is open source is security is 128 bits proven security and quantum resistant. And well, yeah, we're building that for the last 2 years currently. Okay, so but I want to talk a little bit today about the vision that I see from how the future blockchains. I mean, how the blockchain will look like in the future, and it's just a vision. I mean, we don't have the crystal ball, but just want to explain here. So the idea is this important separation between data and execution. We can understand that blockchains at the end is going to be just data availability, maybe blobs, okay? And this data availability will be, when you execute this data, you deterministically, you will get a state or something like that, okay? So the idea is, I mean, a good example, for example, is when you have a normal blockchain. I mean, normal blockchain, you have a lot of transactions. Imagine all the Ethereum transactions from the Genesis block. You could execute, I mean, you could query these transactions, and uniquely, you could get a state, okay? And the cool thing of the ZK thing is that you can do this query, you can get this state, and you can have this proof that you have this state. So when you have a new block, you can use this new state, you can prove the previous block, you get the new data that's in the blobs, and then you get the new state. So this is a way of having also a blockchain, okay? But this extends more to other things. I mean, I not only need to have transactions, I can have maybe attestations or hash of other information there, okay? And here is the concept of what we call dynamic consensus or static consensus. I mean, dynamic consensus is the consensus that will reach every block. I mean, maybe this data that appears in every block. And the static consensus is how we process this data. And this is something that doesn't change. I mean, this is the protocol itself. I mean, how Ethereum processes the transactions is something, well, it changes in the forks, but in general, it doesn't change. And this is the static consensus. So defining a new blockchain can be as easy as defining this static consensus, and you just start putting data, so you don't need to do any fork on the main chain. Okay. Well, I'm gonna assume, but let me explain a little bit, so maybe a specific detail, and this is how this model can be applied to have what we call synchronous composability between rollups, or even between rollups and L1. So what's a synchronous composability? Well, the idea is that if you are if you are executing something in the smart contract, maybe in mainnet on one rollup, you can do a call to another smart contract that's in another chain. Okay, this call may return. Okay, and all this you do it atomically in a single transaction, and this can. Here is 2 chains, but can be 10 chains. This call is maybe it's calling back, it's coming the other. So, but the idea is that you connect the chain just doing a single call. I mean, an opcode that already exists in Ethereum. Okay, so let's assume first. Let's forget a little for a moment for the layer 1. Okay, so let's think about multiple rollups that they want to connect all together. Well, following the original schema that I mentioned before, you can put all the transactions in the L1. So, okay, you have all the transactions. These transactions, they may call one rollup to the other. So they may call, so one transaction may call 3 rollups, and another transaction can call 4, they affect 5 rollups, okay? But what's clear is that if you put all these transactions on chain, you deterministically, you can compute the state of all these rollups as if you execute these transactions in a synchronous way, okay? So you can have the same idea. The only thing is, instead of having one state, you can have like 3 states. But you can put all the transactions that you want in the blobs, okay? And then you just put it in there. Of course, you can put it in mainnet, and you put it together with a proof, okay? So this is a little bit how it would work. I mean, this is a block, so we have 12 seconds of a block. So the idea is that you could build transactions. Of course, there are transactions that may be two rollups, so you need to process the states in parallel, okay? But the idea is that while you're doing this, where you're building this block, you can also start generating the proof, and at some point you can release all the transactions and you release the proof of this. So you can update. This is the idea of the called base rollups here, okay? But this is the idea that you can, in the same block, you are updating many rollups, and all of them, they change the, so all of them, you change the state at the same time, okay? The important part here is that, and this is what enables real-time proving, is that if you put the data and you put the proof at the same time, this simplifies a lot the protocol. Of course, you need to build this proof, which is more expensive, but this is what in ZisK we can do it very well, but this is what allows to improve a lot on that, okay? So now let's go a little bit quick about how you could do that so how can you call from L1 to L2 and L2 to L1, even without forking today's Ethereum. So how can we do this composability between L1s and L2s? Okay? Well, for this, let's put an example here, okay? So imagine that you have a user A. User A is called a DAO, but this DAO contract at the same time is calling maybe a whitelist for saying if he can vote or can vote, and then it returns back, okay? But there are some smart contracts that are running in L1, some smart contracts that are running in a rollup, in an L2, in a rollup. Okay, so the first idea is, okay, we define this idea of proxy contracts. I mean, when you have the DAO that's running in L2, it will be a proxy. This is a counterfactual contract. I mean, it's a contract that's still there, that somehow represents the DAO that's in L2. But it is running in L1, okay? And his address is deterministically. The address is a function of the address of the L2 and the chain ID of the L2, okay? So this is something that's a contract that represents itself, okay? And how this works, okay? Well, the other part is that we are building, so here we will build a set of executions. How we read a table of executions, okay? So what this table means? Well, this table means if the rollup 1 is in the state 0x1111 or whatever, and you do a call, so what happened? Well, you are going to have this new state, and actually the result is going to be this return, or in this case, because it's a nested call, the result is that you need to do a call to another contract in L1, okay? And we continue. So this is, you see the execution, this will do a call, then this will be this part, this is the execution, you execute his whitelist, and then the return, then returns and here. So you have this table of executions that happens here. So how this would work? Well, this special proxy contract, actually what it does, it starts with, so it receives the call, and this call, when this receives the call, actually it do a lookup to this table. It sees that the call is the first line. So actually what it does, it updates the state of the chain. Updating the state of the chain is equivalent to actually executing this state, because this is what it means. And well, the result is going to be another call. So this DAO is going to do the call to the white list. It's going to emulate this call. The call is going to return, okay? And then this return, it will check in this execution is what happened if you execute this execution with the new state. In this case, the 0x2 in there. Well, you get another return, and then this emulates back the return to the user A. So the effect here is that the user is going to be, so it's like the same thing that if they were executing one each other, okay? So how would this process be? I mean, if you are a block builder, you want to execute this. Well, probably these transactions maybe are going to be some meta transactions somehow, but the idea is that first of all, maybe you need to create these proxy contracts. So it's going to be in a single transaction. You are going to create the proxy contracts. You are going to send this state transition function. This state transition function will go with a single ZK proof that all these entries in the execution table are correct, they are following the rules. then you are actually going to execute these transactions following, of course, the calls emulated with proxies that were already developed, that were already deployed. Then you do the, so they will be simulated. I mean, they're going to be executed as it was, okay? And, well, maybe it's a last state that if you want to do more transactions that don't affect rollup, you can put all these together, okay? And all this goes with a single proof that goes together, okay? So this is how it works, okay? The cool thing also of this model is the idea that the rollups, you can define your own kind of rollups. I mean, the rollups, they don't need to be EVM rollups. It can be WASM rollups. So you can define your own state transition function. The main idea is that the state transition function can accept calls and can emit calls. Okay, but the call is the only thing that they need to process as that. Okay, and even that, the cool thing of this is that these calls, I mean, without you can define an app chain. I mean, you can extend Ethereum somehow with the state transitions that you want. They can be private, okay? And even if the state transition function changes or they have their own governance for changing this state transition function, this does not break all the networks. Of course, if there is a malicious network, actuating with a malicious network, it will be wrong. But this will not affect the rest of the chains. It's an exception if this call includes value, it includes Ether, then of course you need to take into account that. So maybe the smart contract in L1 is to keep this accountability, this into rollup on that, but that's fine. I mean, you just bring this accountability so that a rollup cannot call more value than the one that received before. That's the only thing you need to take into account. And yeah, so, well, just a couple of things on that. All this system, it's absolutely orthogonal to preconfirmations. I mean, preconfirmations is another story and can be built on top of that. So if you want to accelerate the blocks, this is for other thing. And also is that what I explained, you don't even need to fork. I mean, we can create that without forking L1. I mean, we can start building tomorrow. Actually, we started somehow to do some work on that. I put here for reference. Here are some work and some papers and some work that we are working on that. And yeah, I mean, coming back a little bit to what this is just an example of many other things that you can use with ZK. And to finish my presentation, just a quick update of the current status of the current benchmarks that we have in ZisK today. We are able to prove in real time with 16 GPUs, we can prove almost all the blocks in real time with an average of 9 seconds. And in the upcoming version, I mean the 0.17 that we probably are going to release during next week, we already expect a 30% improvement there. Okay. Currently, the idea is that this version is going to be frozen, it's going to be stabilized. We need to build a little bit the packaging of all that, I mean SDK and documentation on that. Okay, so maybe 0.18 it will contain all these packaging on top of that, but then we want to focus very much on security and formal verification and making this very provable. Okay, so that's it. That's what I want to explain. If anybody is interested in ZK, please use it. We are here for the community, and we want the community to use it. Thank you very much.